Hello, in this video I'm going to go through what's quite an involved two-dimensional kinematics problem. So we've got 2 dimensions and 2 particles. So this is about as difficult as it gets for kinematics before you head off to university. I'm going to create a table so I can fill it in before while we're going through the question. So we've got 2 particles A and B. So I'll set those up separately. T, S, V and A. We're going to have 0 time at some point for these, and now let's fill in as we're going along. So 2 helicopters A and B. Oh, we've got unit vectors I and J going east and north. Although it doesn't really affect very much what we're doing, but it's good to know. You should specify what your frame of reference is and how it's set up. Both helicopters moving in the same horizontal plane well above ground level, so they're not crashing. At the start of the display, A is at the origin. 0, 0 displacement for A. B is at 40, 50. 40, 50. Velocities of A and B at the start are 8, 4 and 6, 9. 8, 4 and 6, 9. And the accelerations, which they've already told us are constant, are this minus 0.2, 0.1, and for B, it's just the opposite, 0.2 minus 0.1. And they want us to find the distance between A and B at the instant when their velocities are parallel. Right, so parallel vectors you'd have done ages ago, hopefully, in maths. So we want the arrows pointing in the same direction, but it doesn't matter how long they are. The key thing is that these angles are the same, which means we want them to be similar triangles. So the ratio of the components should be the same. We've got our I's and J's, and the ratio of those for each vector needs to be the same for them to be pointing in the same direction, for the velocities to be parallel. So at the time that they're parallel, we're going to need a general form of the velocity at time t. And the velocity is the accumulation of the change of velocity is the accumulation of the acceleration. So that will be 8 minus 0.2t and 4 plus 0.1t. This will be 6 plus 0.2t, and this will be 9 minus 0.1t. So dividing top and bottom in these vectors should give us the same answer when their velocities are parallel. So I'm going to cross multiply these, and I'm going to stick in a factor of 10 to get rid of these annoying decimals that we've got, because it doesn't matter how much we extend, that's all making these arrows longer if you multiply everything by 10, but it doesn't change this angle, so it won't affect our answer. So we'll be doing 80 times 90 is 7,200. We'll have a 1t times a 2t, which is a 2t squared. We're going to have a minus 80t and a minus 180t, so minus 260t. And now we do the other ones. We've got 40 times a 60, which is 2,400. We've got a 2t times a 2 times a t, which is 2t squared. Then we've got a 60t and an 80t, so 140t. So that's just cross multiplying these two vectors as if they were fractions. Cancel the 2t squared on both sides, and then we'll just shuffle around the other bit. So we've got 400t on one side and 4,800 on the other, which means we're going to have cancel all the zeros, divided by 4, t equals 12 seconds. Excellent. So we know the time when all this is happening. Now we need to get the displacement of A and B so we know how far apart they are. Right. So we need this here, which is going to be a ut plus a half at squared approach. I mean, we could fill in this velocity, get that as an actual value, I suppose, and then say, well, what is the average velocity multiplied by the time? But that's exactly the same thing. If you remember back to the red flag on all this stuff is when we're filling in this table, we've got a velocity missing. It's probably best jump into a SUVAT formula. Just saves us a bit of time. So we've got 8 times t, so 8 12s is 96, plus a half of a times t squared. So that's going to be minus a tenth of 12 squared, so minus 14.4. Then for the other one, we're going to have 48 plus, it's going to be plus half this because the magnitude of the acceleration is half of it. So we'll be doing plus 7.2. It's going to make it easier for these. We'll have a 72 plus 14.4. And we've got to add on the 40. We've got to remember for B. And then we'll have 108 minus 7.2 plus 50. So we have to look at the change in, well, not the change because it's two separate particles, the difference in the displacement of A and B at this time t is 12 seconds. Okay, so the difference in the displacement between A and B, so delta SAB, is going to be, what have we got here then? So we've got 81.6. We want the magnitude of this, minus, what have we got? 126.4. So that's that one. And then we're going to have the magnitude of the difference between 55.2 and whatever that is, which is 158 take off 7.2, so 150.8. Right. Yeah. Just make those magnitude signs a bit thicker so we know that they're magnitudes and I'm not writing ones on there, because I'm going to be adding hundreds on everything here. So that is going to be, what have we got then? Difference between those is 44.8. And the difference between these is 95.6. Of course, you could have done all this in a calculator, but it's not rushed to the calculator. Although I will be rushing to a calculator now because we need the magnitude of this. So this distance, so the distance between A and B is going to be equal to the square root of 44.8 squared plus 95.6 squared. And that is not something I really fancy working out on pen and paper. So I'm just typing that in now. We're getting 105.6 meters. So let's say 106 meters, considering the accuracy in the question. Right, so yeah, 106 meters is our final answer on that. So yeah, there's a lot going on in there. That's about as much as you could expect to see. We partly talked our way through it. We still use the concepts. We could have used concepts even more if we wanted, but that jumping in here to get the displacement when we've got the acceleration but not the two velocities is just so useful. That's the best thing that SUVAT gives to us. Otherwise, we're just talking stuff through. But yeah, that's a tough question.